Welcome to this explainer. Okay, I am absolutely thrilled you're tuning in today because we are going to uncover the invisible, highly complex infrastructure that powers modern planetariums and theaters. When you sit down for a show, it's incredibly easy to get lost in the stars above you, right? But today, we're looking behind the curtain to explore the exact engineering blueprints that make that immersive magic possible. Just take a look at this beautifully lit venue space on screen. It feels totally effortless, completely immersive. But actually, getting this magic to happen, it's not just about plugging a few cables into a wall. It's actually built on a meticulously stacked pyramid of strict life safety codes, legacy hardware protocols, and cutting-edge IP networks. So, here's our mental roadmap for today. We'll start with the foundation, move on up to the lighting layer, hit the audio layer, and wrap it all up with the converged system. All right, let's dive right into part one, the foundation, code, power, and segregation. Before any lights even turn on, we have to talk about life safety. There's an absolute rule in systems integration that our source highlights perfectly. Quote, "These control signals are mostly low voltage and will need to be housed in raceways and conduits separate from power delivery." Basically, you absolutely must keep your heavy power and your delicate control systems completely physically segregated. Now, what's super interesting here is how local building and fire codes, like the ones in Denver, for example, explicitly mandate this physical separation to prevent catastrophic fire hazards and ensure signal integrity. We're talking about Class 1 power lines often needing 1-hour fire resistance rated barriers and non-flexible metallic raceways. You literally cannot casually mix these with your Class 2 or 3 low-voltage AV control circuits. And get this, if you're designing a space where flammable vapors might exist, say from a special effect, the code sometimes dictates highly specialized Class 1 Division 1 or 2 electrical equipment just to prevent accidental ignition. It is serious business. Okay, so once we've got all that wiring safely segregated, what happens when we actually flip the switch? Well, starting up a massive projection and audio rig causes a giant electrical surge called an inrush current as primary filter capacitors charge up. To stop sudden voltage sags or falsely tripping your overcurrent protection, we rely on automated sequencing switchboards like this Lintec panel right here. They stagger the activation of high-power branch circuits at really precise intervals because, honestly, tripping the main breakers and plunging the audience into darkness before the show even starts? Yeah, not a great look. Let's break down how we actually build this AV-specific electrical isolation. To completely kill off structural noise and that dreaded ground loop hum from our sensitive audio paths, engineers strictly follow National Electrical Code 250.146D. First up, your standard 120-volt output enters a balanced toroidal isolation transformer. Second, it's split into two 60-volt conductors running 180 degrees out of phase. Third, any common mode noise present on the lines gets symmetrically phase-canceled right at the ground junction. And finally, specialized isolated ground receptacles route a completely clean ground directly back to the service entrance. It's just a beautiful piece of engineering. And just as a quick aside, pulling these complex, code-compliant physical layers, definitely not for amateurs. It requires serious, documented expertise. A journeyman electrician needs 8,000 hours of experience, and a master electrician, they need at least 10,000 hours of earned hands-on practice. To put that into perspective, that's roughly 5 years of full-time work just to legally touch these systems. All right, moving right along to Section 2, the lighting layer, DMX 512-A. Let's unpack this essential acronym. DMX 512A, or ANSI E11, if you prefer the official standard name, is the digital lighting control protocol. It's built specifically to send 8 and 16-bit control data packets from a central controller out to your fixtures. You might hear older systems called DMX 512/1990, but the robust, modern standard we rely on today is DMX 512A. And this perfectly illustrates the hardware side of things. The standard utilizes these standard 5-pin XLR connectors. One pin houses a signal common, while the others provide primary and secondary data links. This exact setup is what allows technicians to cleanly daisy-chain controllers, moving lights, and color changers all across the entire theater. So, let's quickly run through the vocabulary that makes this whole system tick. A universe is a single data stream with up to 512 control channels. The address is simply the starting channel that a specific fixture is told to listen to. A channel is the exact control value, like, say, dimming to 50%, panning left, or turning completely blue. Oh, and whatever you do, never, ever forget the Terminator. No, not the cyborg. It's a little resistor you slap at the very end of your cable run to prevent digital signal reflections from bouncing back and absolutely ruining your lighting cues. 512. I really want to emphasize this number for a second. It represents the absolute maximum number of individual channels that you can meticulously control through just one single DMX data cable in a single universe. It's a remarkably efficient way to handle complex visual data. Which brings us to Section 3, the audio layer, Dante and PTP. You know, back in the day, AV systems were totally separate from data networks. But today, modern solutions like Audinate's Dante run right alongside standard data traffic on commercial network switches. In a converged network, your theater's pristine audio streams are actually sharing the exact same infrastructure as the office phones and computers. It turns AV management into a very familiar, highly scalable task for the enterprise IT department. But here's the catch. Sending audio over a standard network requires flawless timing. Enter PTP. Let's translate this jargon. Precision Time Protocol is Dante's timing synchronization protocol. You can think of PTP as the master conductor of a massive digital orchestra. It ensures that every single speaker across the entire network fires at the exact microsecond it's supposed to. It's what maintains perfect digital audio sample playback. Here's a quick play-by-play of exactly how PTP version 1 pulls this off. First, one single Dante device on the network gets automatically elected as the clock leader. Second, that leader sends out multicast sync and follow-up messages to the rest of the network. Third, all the follower devices receive those messages and immediately fire delay requests back to the leader. Finally, the exact network delay is calculated to lock in perfect synchronization. Amazingly, a single clock leader with just a 1 gigabit connection can keep up to 300 Dante devices flawlessly in sync. Now, for the IT folks tuning in, let's briefly contrast two fundamental networking concepts here. Multicast traffic is sent to all nodes simultaneously. Dante relies heavily on this for that critical clock sync we just talked about, as well as device discovery. Unicast traffic, however, goes directly from one specific device to another. Unicast is really the workhorse here. It's the default method Dante uses for routing the heavy streams of actual audio media. So you might be wondering, how much bandwidth does all this actually eat up? Let's break down the math. For a standard, high-quality, uncompressed 48 kHz 24-bit audio stream, 4 channels of audio get packed into one Dante UDP flow, using about 6 megabits per second. If we scale way up to 64 channels, that translates to 16 flows, using roughly 100 megabits per second. To put that into perspective, 64 channels of pristine audio barely uses a tenth of a standard gigabit network link. There's plenty of headroom, meaning IT departments don't have to go pulling entirely new fiber just to get great sound. All right, let's bring it all together in Section 4, the converged system, IT best practices. If you're the one actually managing this converged network, these are basically your golden rules. First, definitely utilize DHCP for IP addressing to avoid human error with static IPs. Second, and please listen to this one, you must, absolutely must, disable energy-efficient Ethernet. You might know it as green Ethernet or 8023A. Leaving that power-saving feature turned on, it will completely ruin your PTP synchronization and cause terrible audio dropouts. Don't do it. Finally, implement DiffServ QoS, quality of service, to prioritize those tiny, vital PTP clock packets over regular bulk network data. When you lock in those best practices, the whole system just opens up. Thanks to software tools like Dante Domain Manager, our AV systems can literally cross routers over a wide area network. By swapping out standard MDNS for unicast DNSSD for device discovery, we unlock limitless scalability. We're talking about managing audio across massive routed campus networks as if they were just one room. Which brings us to a pretty provocative question to close out our deep dive today. With IT networks now managing literally everything from those strict fire-rated electrical codes we started with to sub-microsecond audio synchronization and even infinite IP lighting controls, what happens to the modern planetarium when AI begins to fully automate these converged blueprints? It's a fascinating future to think about, right? Thank you so much for joining me on this explainer to explore the hidden infrastructure of modern entertainment. Keep wondering, keep learning, and I'll catch you in the next one.